So this Thursday, we're going to have a term exam. So this review pretty much covered the key concept that you covered in the exam. And there's no guarantee that it covers everything we put in the test paper, but I think this basically provides the things that you know that where you want to focus. I think is supposed to cover the most, the majority subjects that we covered in this term exam. Okay, so last class I think we really talked about the functional dependencies, keys, superkey, and also how to derive the closure of separate attributes. And this class can really focus on the normal forms normalization and also design a database using ER model. So for the normal form, so a relation schema in the first normal form, if each attribute of that relation schema is atomic. So by atomic, we mean that for each attribute, every record in that table can have only one value for that attribute. So basically, each record can have only one value for that record, for that attribute, and that value usually should not be divisible. So it means that we do not allow the composite attribute, and we do not allow multi-valued attribute. Multi-value, we mean that for that attribute given record in that relation, that attribute may take multiple values. Okay. Then we also discuss second normal form and third normal form. So basically, a relation schema is in second normal form. It must be in the first normal form first, means that every attribute is atomic. Then if every non-prime attribute in R is fully functionally dependent on each key of R. Okay, so it basically indicates there's no partial functional dependency. So here, partial means that non-prime attribute is dependent on the partial key. So that's very important. You need to understand. Partial FD means a non-prime attribute. Maybe if we think about each non-prime attribute, a non-prime attribute is dependent on a partial key or on a part of a key, but not the whole key. Okay? A part of the key basically means that usually this key must be composite. So instead of dependent on the whole key, all the attributes in that composite key, partial functional dependency means that, okay, it is only dependent on the what? On the part of the key. So that's called a partial. Okay? And we also, for the third normal form, basically the definition is that a relation schema is in second normal form first. Okay? Then we can examine the conditions to see if there's any transitive functional dependency exists. Okay? So this actually slide shows a general normal form definition, means that basically the background theory is that in the database design, when we create tables in a database, we really want to make sure that each table is in at least third normal form or 3.5. Okay, so if a relation is not in third normal form, that means that that relation has some the kind of structure of the relation has some problem. So we need to normalize it. Okay, so that's the basic idea of the third normal form means. So third normal form means the minimum requirement for building up relational database that we can keep or guarantee the good quality of the data. Okay. So this actually shows a generalized kind of a third normal form definition. So given a relation schema and given a set of functional dependencies defined on that relation schema. Okay, so X determine A. So we're going to examine every functional dependencies defined on the R. So the functional dependency is in the form X determines A. So either X is a superkey. So recall that superkey is also superkey contains a key, okay? Or A is a prime attribute. So if X is a superkey, X contains a key, then this X determines A is not partial. It's not partial, okay? The second one is A is a prime attribute of R. So either one of these conditions satisfied, then this that means this functional dependency is okay. So if the first, the A satisfied, that means that okay, this is full functional dependency. Okay, full functional dependency is always good, but full means that a prime attribute dependent on the whole key. If the first condition is not satisfied, that means A is not a superkey. So if A is not superkey, then it can be two. X is not superkey. Sorry, X can be two possibilities. Either X is a partial key, or X is a non-prime attribute. Okay. Then the second condition is A is a prime attribute. So either one of them is fine, then the functional dependency is okay. But if both, because we have either condition, if both are violated, that means that there's something wrong. Okay. So if both are violated, that means that either the functional dependency is partial, or the functional dependency is transitive. Okay, so I think we discussed in the class that a transitive functional dependency, then X determines Y is transitive if both X and Y are non-prime attributes. Okay, so this kind of general normal form definition basically cover both partial, both second normal form and third normal form. But given a functional dependency R, as long as these two conditions are violated, then that relation is not in 3F. But if one of them is still satisfied, that's fine. Okay, if the first satisfied, that means first is a full functional dependency. If first not satisfied, if the second is satisfied, so if A is the prime attribute, that means that the X determines A will not be the transitive, okay? So that's fine. But if both are violated, that means that X determines A is either partial or transitive functional dependency. Okay, so that's basically what this definition is for. So means that in practice, we can use this definition to just simply examine if a relation schema is in third normal form or not. If no, we have to undertake normalization process. If yes, then it's fine, okay? So let's see some example here. So before we see some example, let's see the normalization process. I think in the assignment, I also see some assignments still forgot the step 2. So the normalization process always takes 2 steps. The first one, we simply pick all partial functional dependency and all transitive functional dependencies. Then we're going to create a relation schema for each one of them, one at a time. So that's why in the step 1, for example, if we have 2 partial and 1 transitive, then the step 1 will create 3 relation schema, 1 for each partial and 1 for that transitive. So once we finish handling all partial and transitive functional dependency, then we're going to move on to the step 2. So step 2, we have to create a relation schema, and that relation schema should contain the primary key of the original big relation schema plus if there's any attributes that are functionally dependent on that on the key or the original primary key. So step 2 is very critical. If we miss the step 2 in the normalization process, then our resulting relation schemas are not correct. Okay, so if you try to specify the foreign key and the reference key relationship, you probably realize that you do have some relation schema is not related to any other relation schema because there's no foreign key points to the primary key of the other schema, or there's no foreign key points to the schemas of the primary key. So you have some kind of isolated relation schema has nothing to do with other relation schema. If you find that in kind of that case in your database design, you know something must be wrong. Okay, so let's see the example here. So we have normalization exercise 1. So we have clinic visit. So we have patient ID, patient name, insurance number, doctor ID, doctor name, diagnosis, and date and time. So in this case, we have a composite primary key that contains 3 attributes. Okay, so assume that this primary key is the only key of the schema, and also we assume each attribute is atomic. Then for the 3 functional dependency, FD1 patient ID determines patient last name and the insurance number, and the doctor ID determines doctor last name, and the patient ID date and the time determines doctor ID and the diagnosis. So now the first thing we need to try to examine that what are the prime attributes and what are the non-prime attributes. Okay, so the prime attributes is very straightforward. So if we know all the keys, in this case we do know there's only one key, then we simply list the attributes of all the keys. Okay, as long as an attribute appears in one key, then that attribute will be the prime. So in this case, we have only one key, that is primary key. Then we just simply list its attributes. So all attributes that make up the primary key will be the prime attributes. Then the remaining attributes will be the non-prime attributes. Okay, so that will be the PL name and insurance number and PL name and then diagnosis. I think that's it. So I think we also have doctor ID. I'm sorry, doctor ID is here. Okay, so that's about 5 non-prime attributes and 3. Then list partial functional dependency, intrinsic and full and. So now we're going to see which do we have a partial. Let's start from FD1. So FD1 patient ID determines P name and the insurance number. So we look at the patient ID. So patient ID is not a whole key, but it is a partial key because patient ID, is a member of the key. Here we have a composite key. So patient ID is part of this whole key, but not the whole key. So that's why the first will be the partial. Okay. Excuse me. Then the second one, doctor ID determines doctor name. So now doctor ID is now a partial key. So it means that doctor ID is not a part key because the key only contains patient ID, date, and time. So in this case, doctor ID is non-prime attributes. Then doctor name is also a non-prime attribute. So we have non-prime attributes determines non-prime attributes. So that's actually will be the transitive FD functional dependency. Okay. So the second one will be the transitive. The FD3, patient ID, date, time determines doctor ID and the diagnosis. So here, patient ID, date and time is actually a primary key, so it's a whole key. So then we know that doctor ID and the diagnosis dependent. They are dependent on the whole key. So that's why it's called a full. Full means that a non-attribute or set of non-attributes that are dependent on the whole key. That's called a full functional dependency. So then if we want to list the partial, so we can do the FD1 is partial and FD2 is transitive and FD3 is full. Okay, sorry. So that's kind of the answers. How do you examine the different type of functional dependency? Then which normal form is clinic validity? So since we have assumption each attribute is atomic, that indicates this clinic visit is at least in 1F. Then we need to see if it is in 2F. Then we need to see if it is in 3F. But unfortunately, it cannot be in 2F because of that partial functional dependency. So that's why the clinic visit is only in 1F. Due to the partial functional dependency, it cannot be in 2F. Then if it is not in 3F, then we do the normalization process. Okay, so it is not in 3F, sorry. Then we have to normalize it, okay? So we normalize the clinic visit. So we fully follow the step. So step 1, we simply list all partial and transitive functional dependencies. So we have one partial and one transitive. Then we just create a relation schema for each one of them. So for the partial and for the transitive functional dependency. So I probably will copy this too so that I'm able to clear how I create. Okay. So the step 1 is create a relation schema for each partial and transitive. Okay, so we have one partial. So creating this schema is very straightforward. We just simply create a relation schema that lists all attributes, for example, in the partial functional dependency. So I call it patient info, how about that? Then we simply list all attributes in this FD1. That will be patient ID, patient last name, and insurance number. Okay, so here the attributes are not case sensitive. Then whichever is the determinant will be the primary key of this new relation schema. Okay. Then we move on to the second one. So second one is the transitive. So we're going to create another relation schema for this transitive. So that's going to be the doctor info. Okay. So it has doctor ID and the doctor last name. Then doctor ID will be underlined. Okay. Now we finished step 1. So then we have to always need to have step 2. So the step 2, we simply create a schema that contains the primary key of clinic visit and any non-prime attributes. That are fully dependent on the primary key. Okay, so usually if the question does have a functional dependencies that contains the full functional dependency, so the primary key determine some non-prime attributes, then we can utilize it. Okay. If you cannot find, or if this full functional dependency is not provided, then you have to pretty much first pick the primary key, so patient ID, date, and the time, then find out any non-prime attributes that are not included in the dependent side of the partial functional dependencies or transitive. So I think in the class I show you how to do it. So for example, if FD3 is not given, I think that's very common cases. Then we just based on the FD1, FD2, this one partial and one transitive, we just cross out. So we identify the attributes that are not dependent on the primary key. So we have P name is not dependent; it's actually dependent on the patient ID, and insurance number. That's another one. Okay, because of this both dependent on the patient ID, not the whole primary key. The second one is DL name. So DL name is not dependent on the whole key, but rather on the non-prime attributes. So we have DL name. So this should be. So we cross out these three. So then the remaining two are supposed to dependent on the full primary key. Okay. That should be doctor ID, and so we have probably clinic visit or visit info. So we have patient ID. So that's the patient ID and the date and the time. That's the original primary key. Then doctor ID and diagnosis. Okay, so that's basically depend from the step 2. So okay, so that's basically the relation schema produced by second step, by step 2. Then we also need to list final results. I think that's a good practice because you have to understand after normalization, how do we utilize the results? So we have final results. So these final results basically means that we will no longer use clinic visit that we started with. And then we will replace it with these 3 relation schema created in that normalization process. Okay. So let me shrink the first part. Okay, so then what we need to do is that, so I think in your assignment, I have found quite a few of you didn't, when you list all created new relations, you forgot to underline the primary key, so that's very important. I think I did the same thing. So when I do the second step, I also need to underline the primary key. So it's this primary key of the relation produced in step 2 will be the primary key of the original relation schema clinic visit. Okay, so that's always will be the case. So now we have this 3 relations, and now we have to specify the foreign key. Okay, so foreign key in this case, visit info, the patient ID is a foreign key reference to what? Reference to the patient ID of the patient info. Okay, then the doctor ID in the visit info will be also the foreign key reference to the doctor ID of the doctor info. Okay, so then we have 3 relation schema, 2 foreign key and the reference key pair. So 2 kind of directed arrows. So that's really connect or relate all 3 relation schema together. Okay, so that's the final result. Okay, the second one, I think we have time. So the second normalization exercise. So we have transcript, have student ID, course name, last name, course number, first name, department code, department name, and the grade. So with, with these three functional dependencies specified. So what normal form is transcript in? So it's, I think, before we have these answers, we probably have to first assume. So if we assume each attribute is atomic. Okay, so I think in this class we always make this assumption. Okay, we just simplify the question. Then we have to examine whether the FD1, FD2, FD3 are all full, or if we do have some partial. If we have a partial functional dependency, then that's it. That means no 2F. So this relation schema only in 1F. So we can kind of, I think, if you know to identify the prime attribute, I think it's very easy for us to identify, okay? So for the prime attribute, that's basically the one that's made up in this primary key. So we do SID. So here we also assume each attribute is atomic, and there's only one key in transcript. So that's the primary key in the transcript. Okay, so now the prime attribute will be the SID and the course number. Okay. Then the non-prime attributes will be all the remaining attributes: F name, L name, course name, department code, department name, and grade. Okay. Then with the information of the prime attributes and non-prime attributes, then we can easily identify what is a functional dependency. Is partial, transitive, or full. So the first one, SID, determines F name, L name. So F name, L name are the non-prime attributes. They are dependent only on the partial key, not the whole key. So SID is considered as a partial key because it's a part of the key, but not the whole key. It's not a key, okay? So that's why this is a partial. Then the second one, course number, determines course name, DEPT code. Okay, so this one is also partial because course number belongs to the primary key but not the whole key. So that's why it's called partial. It is part of the whole key. So this is also the partial. Okay. The third one, DEPT code, determines DEPT name. So DEPT code is not a prime attribute because it does not exist, belongs to the key. So both DEPT code and the DEPT name are non-prime attributes. So that's why this is transitive. Okay. So since we have partial, that means that the classroom is so dark, so I barely see my keyboard. So in this case, transcript is only in 1 and F because of partial functional dependency. It can never be the 2F. So prevent it from being 2F. So if it's not in 3F, of course it's only in 1F. Then we do the normalization process. So now you probably know that, I think you should know that in the normalization process, step 1, we're going to create three relation schema, 2 based on the partial functional dependency and 1 based on the transitive. Okay, so if I copy paste. So from the first partial functional dependency, we have like student table. So SID app name, and L name. Okay. So then the SID will be the primary key. So let me put them not into right. Okay. Then I think we can remove that. Now we really do not need need the functional dependency to write to include in step 2. But I just want to show you that each relation schema is actually either based on the partial or transitive functional dependency. So based on FD2, which is also partial, we're going to do, I call it course. So we have course name, course number, I think first, and course name, then DPT code, okay? Then the course number will be the, so I just want to save space, but in the exam, I think you feel free to list them. So the last one will be the DPT, department. I call this department, so we have DPT code, DPT name, so to be consistent. Then DPT code will be the primary key, okay? So this is step 1. Then for the step 2, so basically we're going to create a schema that first contains the primary key of the whole, so maybe the grade report, for example, grade info. So what's the primary key of this original transcript? That will be SID and the course number. Okay, now I think we basically come to the situation that there's no full functional dependency specified. Then we need to identify what are the non-prime attributes that should be included in the last relation schema here. Okay, so then we do the same strategy. So we basically first identify either partial and the transitive functional dependency. So we have 3. Then we basically cross out because those those either partial or transitive functional dependency, transitive or partial functional dependency, the dependents all defined that all those dependents basically means that they are not dependent on the whole key. Okay, so my mind is not working what I want today. So the first name, last name based on FD1. But FD2, the course name and the department code are what? Are the dependent. So we're going to cross out course name and department code. Okay. So the FD3, the department name, okay, it's also cross out. Okay, so what we cross out simply are those dependent on the either a partial or a transitive functional dependency. Now I think there's only grade is left. So that's indicate in the step 3, step 2 we're going to put the grade here. So that's indicate only grade is fully dependent on the primary key. Okay. Now we have final results. So final results, we're going to copy all relation schema. Come on, where's my mouse? Okay, then the grade info. So we end up going to use 4 relation schema to replace the original transcript schema. Okay. Then we just simply need to identify the foreign key and the reference key. Okay, so I think probably always start the last one. So SID of the grade info will be the foreign key reference to SID student. Okay. Then the course number, we reference to this one. Then we still have, if we stop here, now we can tell that department is not related to any relation schema through the foreign key reference key. So we miss one. So I think then the course schema, there's a DPT code that will be the foreign key reference to the department DPT code. Now we have 4 relation schema, 3 functional dependent, and 3 foreign key and the reference key pair, then can relate all 4 relation schema together. Okay, good. Okay, so I think that's pretty much this shows that the other way you can write down your foreign key and reference key. So it's either way. So either you draw directly on the schema, use directed arc, or you can type. Okay, even type, I think this direct arc, always the arrow always point to the primary key. So PK stands for primary key, and FK stands for foreign key. So foreign key always reference to the primary key. So this arrow basically indicate referencing. Okay. So I think then we have a last one, the ER design. So I think in the class we have 2 in-class exercise. I hope that's 2 in-class exercise give you a basic idea of what you need to do in the ER design. So first you read the data description. First identify the entity type. Okay. Unfortunately, I think in your homework, I see some students trying to create their own entity type that are not described in the data description. So that's, I think, a very bad design. So basically, you design only model the things that stated in the data description, no more and no less. Okay, so that's very important. So if you're trying to model more or something that you think that should be included, no, you cannot do that. You have to truthfully follow the client, the description or description you're given. You do not need to use your imagination. So that's designing is not the practice that you can use your be creative. Okay, so means that only model whatever is stated in the data description. Never model anything that not stated in the data description. Okay, so I think for this data description, it's very simpler because kind of pretty much help you organize the entity types. So first one, doctors, including their name, room number, and specialty. So basically, we have to include in the database. We have to include the information for the doctors. So we know that doctors is what is entity type. Then the nurse, again, including the names ID. Each nurse has unique. So that indicates for the nurse, we can also model it as the entity type. And the patients, so include their names, address, and name of their insurance company. So that's another one, means patients is also entity type. Then the patients are each assigned to a ward, so a room. So the dates that a patient was admitted to and discharged from a ward needed to be reported. Okay, then a ward is described by the ward number and the building number. So this means that a ward is also an entity type. Okay, then we model doctor, nurse, patient, and a ward. Then a patient are assigned to a ward. So this actually can be considered as what? As relationship type. Sorry. So I think this one does not have so. So this indicates, maybe I use red, indicate this described relationship type. Okay. Then Each nurse is assigned to 0 or more wards. Each ward has at least one nurse assigned. Each doctor is assigned to 0 or more patients. Patients may not or have doctor assigned, but they may have one-on-one doctor. So I think this actually describes the relationship. So each nurse is assigned to one or more wards, because nurse is an anti-type, ward is another anti-type. So this description really indicates there's a relationship between the nurse and the ward, okay? And each ward has at least one nurse assigned. So this not only describes the relationship between the ward and the nurse, but also help us to maybe determine the, for example, maximum number of the nurse that each ward is assigned, can be assigned, at least one. So that can help us to determine the relationship constraint, okay? Each doctor is assigned to 0 or more patients. So this, I think this sentence not only tell us the relationship between the doctor and nurse and patient, but also tell us some information about, for example, cardiac issues, okay? Patients may or may not have a doctor assigned. I think that's the same thing about relationship constraint. Then they may have one-on-one doctor. So here I think what else we identified? I may miss one. I think there's one word. Okay, I think that's pretty much true. So then based on the data description, we can come with first 4. The doctor, nurse, patient, and the ward, okay? Let me see if I'm able to open that data description again. So, let me make a copy. Okay, so I forgot to save that anyway. Let me save back so that we can discuss better. Okay, so now we can open both to show them. Show the data description. Okay. Show the design and the data description. Yeah, I'm able to view it pretty clear. Okay, now that's kind of what we have here. Okay, let me see what's. Okay, so I don't know. Sorry, I couldn't see. I think for some reason, I don't know if I only see 3 messages. So that's in the beginning of the class regarding if you can hear me, but I didn't see any other messages. I just wonder, at least from my side on the Blackboard. So, okay, thank you. So I think one thing that when you text message, you probably can, I think you can decide who you want to text. So please forward to me. Yes, thank you so much. I don't know, something may be wrong with Blackboard. So, because usually if you type message, basically I'm able to gosh. So I saw your message, but still it didn't show up in my message kind of message box. So it's more like a transient. Just show me and then right away disappeared. What's wrong with it? Sorry. So yeah, regarding the Dennis, yeah, I'm going to reply to you after the class. I think since it's so, how do I say, so troublesome. So I do have a couple of students, online students, have trouble to find the local, either local product and service. I think because it's spring break or something, or that's the proctor and services working off work hours, like after this, like 6 p.m. or during the weekend. So I think that's kind of one thing. So that's why I'm thinking for the remote student, I may want you to use lockdown browser. And for the in-class student, I really want them to come into the class because so far we didn't have, there's kind of a, I want to see our student because so far I didn't see all the students in my class, in-class student. I even don't know who they are. So they are going to come into the classroom to take the exam. Okay, so yeah. So I'm going to respond hopefully by after class by today, by this evening. Okay, good. So let's move back to the design. So once we identify the four, then we just need to specify the relationship type described or inferred from the text. I think there's a relationship between the patient and ward. So the patient can, for example, stay in the ward. For example, let's see. So we have for example, patient stay in the so this should be stay. So patient stays in this is the feature I don't like. Okay, stays um, in walls or admitted, whatever the name you want to give. Okay. Then we also have each nurse assigned to 1 or 0 wards. So that indicates there is a relationship between the nurse and the ward. Okay. That's kind of works in the ward. So nurse working in some wards. Okay. I think that's basically simply based on the daily description. So I have nurse, relationship between the nurse and ward. Okay. Then I think we also have like the doctor is assigned to 0 or more patients. So there's another relationship between the doctor and the patient. Doctor sees patients, what verb. So you can give any name you want. But usually we use the verb representing the name for the relationship. Okay, I think that's pretty much it. So now the next one, we just need to identify the relationship attributes or constraints. So I think we do have a relationship attributes. So when we're talking about the patient, so when patient each assigned to a ward, then the days that the patient was admitted to and discharged from ward need to be recorded. So I think here the best place will be the stays in. So you can put the days admitted and days discharged as attributes of the patient, but this may not be the very good one in the sense that if patient maybe come and go, so leave maybe this week and then readmitted next time. So then you can tell that you're going to record multiple days. So that might not be the best way to model it. So the best way to model it, basically we're going to add two attributes for the stay, okay? One is for the in, the other one is for the out date, okay? I can't, sorry. Oh. In date. Okay, so we're gonna give a better name. And then we can also have another attribute to report out date. So out date, okay, so that's basically consistent. Then we simply connecting these two to the staging. So once again, relationship can carry attributes, okay? And also, I think when I'm grading your assignment, I do see that some students tend to model weak anti-type. So weak anti-type basically is not very common, meaning that maybe majority of your design actually do not have weak anti-type. So you'll be aware that you do not need to have weak anti-type in your design unless it is necessary. Okay, I think the next one we just simply define the constraints. Okay, the constraints of the relationship type, like doctor sees the patient. So each doctor is assigned to 0 or more patients. So that's very clear if we use minimum maximum notation. And so the minimum will be 0 because it will assign to 0 patient, and the maximum will be n. Okay, so that's kind of the constraint. Minimum maximum notation for the patient. Okay, based on here. Let's see, each patient may or may not have a doctor assigned. They may have more than one. So that indicates the minimum maximum notation for the patient for this cis relationship is the same. 0 means that a patient is not assigned to any doctor or did not see any doctor. N means that it may see multiple, okay? Then between the patient stay in the ward, I think when we record patients, each patient each assigned to a ward. So that indicates a patient. In this case, we merely model I think the inpatient here. So means that the patient we report in this database will be the one that will be admitted to the ward. So that's why the minimum will be 1 because each patient assigned to a ward. So they have to be assigned to a ward. So that's why the minimum ward a patient is assigned is 1. How about the maximum? I think maximum will be the common sense. So usually we probably have to see that a patient can stay in only one ward. Okay, so that's why the maximum will be 1. Okay. Then regarding to the ward, a ward does it didn't say anything about how many patients can be stay in a ward, right? Let me see what else. A ward is described by ward, not building number. So in this case, we can do our own assumption. So we can either, I think, a ward maybe has 0 patient, and the maximum we have multiple patients. Okay, but anyway, for this one, we have to make assumption because maybe they only try. Because I know that in the hospital setting, we may have kind of a semi-private, so we may have a room shared by multiple people, at least 2 people, or we may have a room only used by a single. So in this case, depending. Okay, so we can assume that depending on assumption. For example, if I assume each ward can have more than 1 patient. Okay, so that indicates the maximum will be the multiple. And number 2, that sometimes a ward maybe doesn't have any patient. Okay, so that's why the minimum will be 0. So it means that ward is empty. Okay, so then between the nurse works in the ward. So each nurse is assigned to 0 or more wards. Each ward has at least 1 nurse assigned. So that means given a ward, the minimum number, the ward participation for the vaccine, the minimum will be 1. That indicates each ward has at least 1 nurse assigned. Maximum may indicate maybe more. Okay. Then the minimum maximum for the nurse, a nurse is assigned to 0 or more wards. So that's really very clear that the minimum maximum notation for the nurse will be 0n. Okay, so that's kind of I think that's kind of the minimum maximum notation to describe the constraints for each relation in this design. So we do have 2 assumptions. So those 2 assumptions are the information we cannot import from the data description, but we have to use in order to determine the relationship constraints. So another thing I want to emphasize that for the relationship constraints, you either use this minimum maximum notation, or you use this kind of the relationship type and constraints. Minimum maximum notation. Okay. Using, so this is the one. And this one, I think I can copy paste. Then using coordinate ratios, participation constraint. So, sorry. Let me make it smaller. We can read it. Okay, so this shows that we can, when we design, we either use the minimum maximum notation or use coordinate ratio and the participation constraints, but we do not use both. Okay, so in this case, we have to specify the numbers if we use coordinate ratios. That will be numbers. So this number actually indicate, given the patient, how many, the maximum number of doctors that patient can be assigned to. So according to the data description, that's n. So this n corresponding to this small n, okay? Then the same thing, so the number on the patient side actually indicate, given one doctor, how many patients that one doctor can see. So that will be the multiple. So we use n, okay? Similarly, since a doctor, according to the data description, a doctor may not see any patient. So a doctor is assigned to 0 or more patients. So that's why the participation of doctor for the Cs will be partial. And the same thing, the patient may or may not have a doctor. So that's why the participation of the patient will be also partial. So that's why we have both single line here to indicate doctor's participation is partial and the patient participation for Cs is partial, okay? Then when we come to the patient, okay, so for the coordinate ratios, if we describe how many wards that a patient can stay during a specific time, that will be 1, okay? So that's why we put 1 here, indicate a patient can stay in 1 ward, okay? Then for how many, then the number on the patient side describe that, given 1 ward, how many patients can stay in that. I think according to the assumption, we think that's n, means that ward may have multiple patients in it, okay? Then regarding to the participation, so each patient each assigned to a ward, that indicates every patient will be participate in this staying to relate to the ward that it stays, he or she stays in. So that's why the participation will be total. Okay. Then for the ward, so since we have a ward does not have an may not, sorry, it's not. It's basic assumption may not or may not have any patient. So that indicates the ward participation will be partial, means some ward has patient, some does not, okay? Then for the nurse work for the ward, so each nurse is assigned to 0 or more wards, so that really indicates, given the nurse, it can work in multiple ward, okay? Then given the ward, I think, do we have a ward? Yeah. Each ward has at least 1 nurse assigned. So that indicates a ward maybe have 1 or maybe more. So the maximum number will be more. So we can use capital N. Then regarding to the participation constraints, so each ward has at least 1 nurse assigned. So the minimum is 1. That really indicates each ward must participate in this worksheet to relate to at least 1 nurse. So that's why the participation of the ward will be total. Okay, so means our ward has to relate to some nurse. Okay, then a nurse, each nurse is assigned to 0 or more wards. So then the nurse participation will, in this case, will be partial. So we use single line because a nurse may not assign to any ward. Okay, so maybe a nurse is not working in the ward, is maybe working in other places. So that's why the participation will be partial here. Okay, so in your design, you either use this one to specify the relationship constraints. So coordinate ratios, 2 numbers, plus participation constraints, either single line or partial line. Or you use minimum maximum notation. Okay, so this kind of this is basically the option you use. Either use minimum maximum or use coordinate ratios plus participation constraints, but do not combine two because those considered unprofessional, either redundant or make your design look very inconsistent. Okay? Okay, good. Any questions? So I think this is pretty much for the term exam review. So I think we covered two chapters or two subjects, relational data model and entity relationship design or entity relationship model. So these kind of two focus we're going to cover in the term exam. Okay, good. So any questions? Okay. If you don't have any questions, then we are done for today. And thank you. Okay, good. So very good question. So I think we have one question asking to if you need to prepare the SQL programming. No. So because we haven't started SQL programming yet, I know some of you may be very proficient. Some of you may not have experience in heavily coding in SQL and PLSQL, so that the programming is not covered in the term exam. So term exam only covers the relational data model and ER model, so no programming. So the term exam, I think, lasts 75 minutes. Okay, so that's kind of the requirement. Just in the next class, the whole class time. Okay, good. So I think for the students who in the 9H1. Okay, so let me see the part. So how did you determine the in and out date were to be assigned with this, associated with the stay? Because that's kind of the thing that we need to report the patients that admitted to the ward and the discharge from the ward. So that's the in date and out date. Okay, so I think you can think there are three places we can put in date, out date, either as attributes of patient, or as attributes of ward, or as attributes of stays, because in date, out date related to the in date and out date of a patient that's staying in a ward. So then you think about if I put in date, out date to the patient, it may not that convenient because a patient may come to hospital many times, maybe one at one time, maybe multiple times. So then this in date and out date, if you record it, you're going to record multiple times, okay? And that might not be kind of convenient. So if you put the in date, out date in a ward, so then this also, you think about if you create a table, you have ward ID in the building, then you're going to have a long list of in date, out date because the ward has so many different patients staying over time. Okay, so then maybe the best thing is put as the stays. So for every kind of a stays instance, relationship instance, so every stays relationship instance relate a patient with a ward. Then we assign in date and out date so that this in date, out date is very clear to be associated with a specific relationship instance. But anyway, so in date, out date will be append to each relationship instance. So that's why I make the this in date, out date, the meaning is more, I think, more meaningful, or how do I say? It's more accurate. So it's related to a specific patient and a specific ward for a specific stay. Okay. So for example, if I stay admitted in the hospital at two separate times, so every time my name, my information with whichever ward I'm staying in will come with in date, out date. Next time I have same information, but I may admit it to a different word, then the indent audit will be appended to that specific state. So that makes this indent audit, the semantics much clearer and accurate. Okay. Okay, good. Any other questions?